All right, so what you guys get for the standard deviation of this discrete random variable?
1.4.
1.4. Anybody else get 1.4? Everybody good with 1.4 and how to get 1.4? All right, cool. Then let's move on to the next example. So again, here in this problem, we have a probability distribution table. The first thing that it's asking us to do is to find the probability. Well, let me take a step back before we do this right here. I know you guys are going to know the answer to this question, but usually the way that these types of questions start on an exam is like this number right here would just be a question mark, right? If that number right there, or any one of the numbers, is a question mark, how could you figure out what question mark is? Add them up and subtract from 1. So then we would get 0.1 plus 0.4 plus 0.3 plus 0.05 plus 0.05. We would add up all of these things and subtract it from 1, and that would then be equal to the probability of 3. So then if we do all this, then just like I crossed away right here, we're just going to get that this comes out to 0.1. All right, so everybody good with that first step? All right, we haven't done that in a couple of classes, so I just wanted to jog everybody's memory about that. All right, so now for A, if we're trying to find the probability that x is strictly greater than 0, but less than or equal to 4, just like I did last class, let's start off with, first tell me, without telling me what the probability is, what values can x take on if it's strictly greater than 0, but less than or equal to 4? 1, 2, 3, or 4, right? So 1, 2, 3, or 4. So this is the same thing as asking us what is the probability of the number 1 plus the probability of the number 2 plus the probability of the number 3 plus the probability of the number 4. Right? Is everybody good with this? And if you do this arithmetic, what do you end up with? 0.85. Is everybody good with 0.85? Any questions about A? All right, and then B. What is the average number of children 18 years old or younger in this small town? So, what is it asking us to do here? Find the mean, find the average, find the expected value. And if we want to calculate out the mean or the expected value or the average, how do we go about doing this? Good. We're going to multiply each x by its probability, by its p of x. And after we multiply each x by its p of x, we're going to sum up all of those, and that's going to give us the expected value. So we're going to say that mu, or the expected value of x, is 0 times 0.1 plus 1 times 0.4 plus 2 times 0.3 plus 3 times 0.1 plus 4 times 0.05 plus 5 times 0.05. And if you do all of this, what do you get? 1.75. Anybody else get 1.75? Cool. 1.75 it is. Any questions about how to calculate out the mean or the expected value of a discrete random variable? All right. Then take a minute or so for yourself and see if you can calculate out the variance of this discrete random variable. So you're not allowed to print it off and bring it with you, if that's what you're asking.
No. If we just solve it on the calculator.
If you solve the problem on the calculator, that's completely fine.
Like we figured out how to do it.
Yeah, exactly. So if you teach yourself how to use your calculator and you can do the stuff on your calculator, that's completely fine. I don't care if you're doing these things by hand or if you're using your calculator to do it. You just can't bring additional stuff
like,
with you.
If you practice, like after class.
Yeah, exactly.
So I kind of figured something out, and I'm just like, I'm going to go with the calculator.
Yeah. Calculator's pretty easy.
I'm not mess up in basic math anymore.
Okay.
No, seriously, I'll do something simple like that. It comes out all wrong.
All right. Yeah, I mean, if you can do it on your calculator, then you'll definitely get the problem right. I'm not going to hold that against you. All right, what you guys get for the variance? 1.71. And that's the variance. That's not the standard deviation. So is this the standard deviation?
Yeah.
All right. So then you have to square. So then what do you get if you square 1.71? 2.9? Yeah, 2.92. So everybody's good then that 1.71 is the standard deviation, and then 2.92 is the variance. I didn't calculate this out, so I'm kind of relying on you all. All right, everybody good with how to get 2.92? Any questions about this whatsoever? All right. Then let's move on to the next section of Chapter 4. And the next section of Chapter 4, it's actually the last section of Chapter 4, deals with the binomial distribution. So for the binomial distribution, we're going to do a lot of this section. But there's one aspect of the binomial distribution for which we need to use a table. We're not going to cover that right now. And it's also not going to be included on your second exam, right? We're going to look at it towards the end of the semester, or at least after we finish up Chapter 5. Because here's the thing. We're also going to use a table in Chapter 5. And we're going to use the table in Chapter 5 then for the rest of the semester. So I want that to be the first table that you learn how to use, because you're going to be using it a lot more. So I want you to feel really comfortable with that table, and I don't want to confuse you with two different tables, because they're similar, but they're also really, really different in a couple of aspects. So what we're going to do is we're going to do as much of Chapter 4.3 as we can without the table. Then we're going to learn Chapter 5. Make sure that you're comfortable with that other table, and then we're going to come back and we're going to look at the table that we need for Section 4.3. Depending on how much time that we have, we'll either look at that other table, so the one for Section 4.3, either before the next exam, or if we don't get to it before the next exam, we'll just push it later on into the semester and maybe do it towards the end of the semester.
I like how you keep pushing it back.
Yeah, just keep pushing it back. Just push it back until after August 6th or whatever it is, whenever this class ends. Yeah, just push everything back, right? Why not? And then we can go to the pool, right? That's what we talked about the first day of class. Like,
I'll joke aside, but I think it's cool because like me, honestly, just including like the most important things that you feel is relevant to study. Because I noticed that with some classes, like in general, they can just leave out extra things that normally would be mentioned.
yeah, the thing about this class is it's supposed to be an introductory level class, right? So you're supposed to get like just a broad picture of stuff that's going on. But whenever you're talking about the broad picture of things, like there's some things that's just like, hey, even though it's a broad overview, like these things are important, right? And what I want to make sure that I do is, there's some people in here that I know this is probably going to be your last math class that you ever have to take, and you just want to get through it so you can continue on with your major. But then there's probably some people in here too that want to take additional stats classes or going into like stats heavy majors. So I want to make sure that I set those people up for success in subsequent classes as well. But all right. That being said, Section 4.3 deals with the binomial distribution. So Let's first read over this definition for the binomial distribution. There's actually a whole lot of stuff that goes into it. And then once we read over this definition, we'll break it down to make sure that everybody's on the same page. All right, so suppose there is a random experiment that has the following characteristics. There are n identical and independent trials of that experiment. There are exactly 2 possible outcomes. Usually we refer to those as success and failure. And the probability of success on any trial of the same is the same number, p. So here the probability is always going to be the same number, p. Then the discrete random variable x that counts the number of successes in the n trials, so we're going to count the number of successes in n trials, is a binomial random variable with parameters n and p. We also say that x has a binomial distribution with parameters n and p. All right, so let's think about this here. Talking about a binomial random variable, the most important thing to realize is that whenever you're reading through a problem, if there is a scenario where there are only 2 possible outcomes, chances are you're dealing with some kind of binomial distribution, right? Just as a quick side note, and this is not something that you have to remember, but what we're going to say here is that if you have some experiment where there are only 2 outcomes, technically speaking, this is a Bernoulli random variable. And we'll see why that's the case here in a second. All right, so whenever we're dealing with something that only has 2 possible outcomes, we're going to go with the verbiage of the textbook, and we're going to say that this is a binomial random variable. What are some examples of an experiment that only has 2 possible outcomes? 2 and only 2. Flipping a coin. That's a textbook example of a binomial random variable. What else? Anything that's either true or false, for example. Okay. What about if there's either one thing that happened or the other thing that happened? What would be an example of that? Winning or losing the lottery, right? Like let's say you play the lottery and either you win or you lose, right? What else? Rain or no rain, right? There's no in between. Either there's precipitation coming from the sky in the form of water or not, right? So it's either raining or not raining. What else?
What about like a gender reveal?
A gender reveal, right? Either it comes out with pink or blue, right? Like if you stick to those 2 colors. What else? Pass or failing, right? You guys get the gist, right? Either you vote or you don't vote. You dyed your hair, you didn't dye your hair. You need glasses, you don't need glasses, right? That might be a little bit more subjective, but you guys get the gist, right? Only have glasses or don't have glasses. That's probably a little bit better, right? So everybody gets a gist. There's exactly 2 outcomes and only 2 outcomes, right? So whenever we're dealing with that, the book is calling that a binomial random variable, right? Now, technically speaking, like I just said, those are Bernoulli random variables. So let's take a step aside and see what's the difference between a binomial random variable and a Bernoulli random variable. If you only flip a coin once, right? Let's go to, like that's our experiment. You're flipping a coin once. You can either get heads or you can get tails. That's Bernoulli. But now what happens if you say, hey, I'm not going to flip the coin once. I'm going to flip the coin 5 times. Well, now what you have is you have a succession of Bernoulli random variables. You have 5 of them. And whenever you have a group of Bernoulli random variables, that's what we call binomial, right? So Bernoulli is just like one trial of the experiment. But if you do that experiment many, many times, now you're coming up with a binomial distribution. Right? Does that make sense to everybody? So what we're dealing here in chapter 4.3 is we're not just going to look at individual trials. We're not just going to flip a coin once and see what happens. But we're going to string these things together. So that's why your textbook focuses just on the several trials of the experiment. It doesn't just focus on that one thing. All right. So that's why this definition is correct, because here what we're talking about is we're talking about an identical trial. So your textbook immediately goes to having more than one trial. But I want to make sure that everybody understands that if we just did one trial, if n were 1, then that would just be a Bernoulli that wouldn't be line. Right? So it should, my opinion is that your textbook should have been specific about the fact that n has to be strictly greater than 1. That's a technicality, right? Is everybody good with if we're stringing together Bernoulli random variables that we end up with? All right, so let's take a closer look at that. So what we now agree is that we're going to have two outcomes, only two outcomes, and exactly two outcomes, right? And we're going to do this thing several times. Now the important thing is this. Let's say that I flip this coin, and let's say the first coin that I flip is fair, right? Then every single time I flip a coin after that, that coin also needs to be fair, right? It needs to have 50% heads and 50% tails. What I cannot do is I cannot flip a fair coin on one trial, and then on the second flip, I flip a not fair coin, right?
Like a heads.
Yeah, like a heads, or maybe it's like a weighted coin where like heads happen 60% of the time. Like, doesn't make sense to me like conceptually, but heads happen 60% of the time and tails happen, like I don't know what a coin would look like, but you get the gist, right? That if on the first flip I get 60% heads and 40% tails, and on the second flip I need to get 60-40, on the third flip I need to get 60-40, I can't change off and go 60-40, 50-50, 60-40, 50-50, or anything like that. Right, does everybody get the gist? So then what we're saying is that if we only have two possible outcomes and exactly two outcomes, the textbook is calling this either success or failure, or as we're calling it, like heads and tails, right? And then the probability of success, or the probability of heads, has to be the same number P. The probability has to say 6 or 50. Right, is everybody good with that? So what this is basically telling us here is this. We're going to have two outcomes and only two outcomes. We're going to do this thing several times, and the probability of getting heads, it has to always stay the same. Everybody good with a binomial distribution? Those are the characteristics. So the most commonly asked question that I always get whenever people are trying to work on a binomial random variable problem is, I always get the question of, this problem doesn't have enough information in it, right? People start reading the problem, they'll be like, there's just something missing here. Especially on a test. Because as you start going through these problems, what always happens is you're going to get yourself in the mindset of doing section 4.3. So as we're going through section 4.3, you're going to get the gist of it. But then once you get onto a test, the problem's not going to say, this is a section 4.3 question, right? So you're going to have to distinguish, what do I have to do for this problem, right? So if you get to a question on the test, right, and all of a sudden you're just like, there's something missing in this problem, I need additional information. Remember that. Ask yourself, are there only two possible outcomes in this problem? And if there are, well, now you know that you're dealing with a binomial question, right? So your first indicator should be there's not enough information in this problem. And if you run into that, ask yourself, are there only two possible outcomes? And then you'll be back on track. All right, is everybody good with this? All right, so now let's take a closer look at how to calculate out the probability of a binomial random variable x. So the formula to calculate out a binomial random variable x is this formula right here. This is to calculate out the probability of it. Then mu, what does mu stand for again? The mean. So here this is going to be our formula for the mean. Here this is going to be our formula for what? The variance. And here this is our formula for standard deviation. All right. So let's take a look at what these different things mean. In our definition up here above, what does little n stand for? The number of times that we're like flipping the coin, right? So the number of times that we have the trials. So little n is going to be the number of trials. Slightly different than what we said little n was before, right? If you remember before, we said that little n represented what? In chapter 2, what did little n represent? The size of the sample. So here now we're doing a little bit different. It's similar. It's not necessarily the size of the sample. It's just the number of trials, the number of times that we're flipping the coin. Right? What does P represent? Probability of?
Success.
Awesome. Probability of success. And we can define success however we want to define success. In some problems, you'll see that success is the probability of heads. In some problems, you'll see that success is the probability of tails. It's always going to tell you how success is defined. And then however success is defined, that's just going to be equal to P. Right? Is everybody good with that? So, especially like, if you look at people who are wearing glasses. Good question?
I was going to say, so would success just be like the probability of whatever outcome you're looking for happening? Like, could a success be like someone failing something?
That's exactly right.
Okay.
Yeah, and that's how they mess with the wording, right? So, success can be whatever you're looking for. It doesn't necessarily have to be something good.
Success is like getting the outcome that you want.
That's right. Success is getting the outcome that you want. So you could say, let's say I'm somebody who sells glasses, right? And I say, hey, success to me is walking into a room where 99% of people are wearing glasses, right? Because then I'm thinking cha-ching, right? So however you want to define success is completely however you whatever the wording of the problem is. All right, and then if we look down here, because in this formula, we also have Q in here. So here defines what Q is, and Q is 1 minus P. So Q is 1 minus P. So if you wanted to put that into words, what does Q represent? The probability of failure. Awesome. The probability of failure. Probability of failure. So if you take 100% or 1 minus the probability of success, then you're going to get the probability of failure because we only have 2 possible outcomes. Is everybody good with that? Then the only other thing that we really need to know in this formula is x. So let's take a look at what x represents. Let's say that I tell you that flipping a coin and getting tails is the good thing. So that's what I'm going to consider to be success. And I'm going to flip a coin 10 times. Right? Now if I ask you, okay, how many, or what's the probability of me getting 7 heads? Now I just gave you an additional piece of information, right? That number, the number 7 out of 10, that number 7, that's what we're going to use for x. So that's what you can think about that as the number of successes that you're looking for, right? So again, if you flip a coin 10 times, you have 10 trials. I'm going to tell you that getting tails is success. So I'm going to give you some probability associated with that. From that, you should be able to calculate out the probability of failure. And now if I say, hey, I'm flipping a coin 10 times, I want to find out the probability that I get 7 heads, then you can think of x as being the number of successes. Everybody good with it?
Reason this x in the same way that we would define our z-score. Given this value, you want to find the z-score at
Yeah.
this value, that would be it.
Exactly right. So you can really compare it to z-scores where you say, hey, this is the thing that I'm trying to convert. So I'm trying to convert the number 7 into a probability. And then now we're just going to use this formula instead of this email. Yep, that's exactly right. So it's just an input to the formula. Awesome. Everybody good with this so far? Now the only thing up here in this formula that we haven't talked about yet is this exclamation symbol, right? Does anybody know what this exclamation symbol represents? You're kind of close. It's not adding. You multiply them. Does anybody know what this formula or the symbol is called? Not quite. No, it's factorial. It's called the factorial. So the factorial, that's how you call this exclamation sign. So if you see the number, say, 4 factorial, see the number 4 factorial, what this doesn't mean is, it doesn't mean 4! Right? You don't yell the number 4. Instead, what we want to do is we're going to take the number 4 and we're going to multiply it by every whole number less than the number 4 all the way down to the number 1. So 4 factorial is the same thing as 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24. So therefore, 4 factorial is the same thing as the number 24. What about the number 5 factorial? What's the number 5 factorial equal to? 120, how'd you get that? You saw it earlier, right? Awesome. So we're going to take the number 5 and multiply it by every whole number less than it all the way down to the number 1. Technically, you don't have to multiply it by that number 1 since it's just the same thing, but I think you guys get the gist. And that's going to give us 120. Everybody go with what factorial then represents? All right. So now we know all the stuff that goes into this formula. We know what n is, and we know how to calculate out n factorial. We know what x is, so we can calculate out x factorial. Here, the order of operation is we simply just do what's in parentheses first, right, as we always do. So we're going to subtract these two things first, and then whatever number that gives us, we're going to have the factorial there. Then in between here, this is all multiplication, right? So we're going to have times p to the power of x times q to the power of n minus x. So even here in the exponent, we're first going to do n minus x, and after we figure out what n minus x is, then we're going to raise q to that power. All right, does everybody go with at least the gist of this formula? We're going to apply it and then see, make sure everybody's on the same page. All right, so let's do it. 30% of shoppers pay with cash, and the remaining shoppers pay with plastic. What is the probability that exactly 3 of the next 12 shoppers will pay with cash? All right, so let's do it. So let me first ask you this. How do we know that this is a binomial question? Awesome. We know that we either have cash or plastic. So we only have 2 possible outcomes, and we have exactly 2 possible outcomes, right? So therefore, that's like your number 1 giveaway for this being a binomial question. So we're trying to find the probability of something happening. So whenever we're trying to find the probability, which one of these 4 formulas are we going to apply? The first one, like the ugly one, right? We're going to try to apply that ugly one. All right. Well, whenever we're trying to apply this ugly formula right here, we need to know what these 4 things are right here. N, P, Q, and X. So let's first try to identify those 4 things, and then we'll plug them into our formula and we'll do the arithmetic. All right. So n, little n, represents the number of trials, the number of things that we're looking at. How many things are we looking at in this problem? 12. The next 12 shoppers, right? So we're going to look at 12 things. So therefore, n is going to be equal to 12. Then here we're saying that 30% of shoppers pay with cash, and the remaining shoppers pay with plastic. What is the probability that exactly 3 of the next 12 shoppers will pay with cash? So therefore, cash is what we're defining to be success, right? That's what we're looking for, so that's what we're going to define as success. So that therefore, if paying with cash is success, what's the probability of success? 30%. Everybody go with this? Well, if the probability of success is 0.3, what's the probability of failure? 0.7. And now what we're looking for is X. How many shoppers are we looking for to have success? 3. 3 of the next 12 shoppers. Everybody go with this? All right. Then let's plug it into our formula. So then we're going to say the probability of X is equal to, I'm going to first copy down this formula. And I believe that this formula is on your guys' formula sheet. So this is not necessarily something that you have to memorize, but it always helps. All right, so then let's plug in the numbers. All right, so we said that n was equal to 12. X was equal to 3. So we're going to have 12 minus 3. We're going to have p, which is 0.3, to the power of 3. And then we're going to have q, which is 0.7, to the power of 12 minus 3. Getting to this point right here, that's the majority of the work. Is everybody good with getting to this spot right here? Any questions about how to get to this spot or why we're trying to get to this spot? How do we get 30%? This one right here? So what we said here is this. We said that we're going to look for the probability that exactly 3 of the next 12 shoppers are going to pay with cash. So we're saying then that we're looking for the people who pay with cash, so we're going to consider cash to be success, right? But then up here in the first line it says 30% of shoppers pay with cash, and that's where we get the 30% from. Good? Awesome. And then because we got here 30% of shoppers pay with cash, then if Q is the opposite of success, if Q is failure, then we just had this equal to 1 minus 0.3. That's how we got Q. Good? Everybody else good with this as well? Any other questions about this? Is everybody good with how to read the problem, realize that it's a binomial problem because we only have 2 possible outcomes, realize that it's asking us to calculate out the probability. This is our formula for calculating out the probability. And then identifying these 4 things and plugging them in right here. Is everybody good with that up until now? Because really what we're doing at this point then is just arithmetic, right? Because now that you guys know that this right here is factorial, that's really nothing more than just a bunch of multiplication. So all we really just have is multiplication and division and subtraction. All right, so let me rewrite this as 12 factorial divided by 3 factorial. What is 12 minus 3? 9 factorial. And then we have 0.3 cubes and 0.7 then also to the power of 9. So here I have it simplified slightly. All right. One of the, another one of a hurdle that a lot of people struggle to overcome is if you start plugging this into your calculator, 12 factorial might be okay for your calculator, right? But if you start having like 25 factorial or something like that, those numbers just get to be so huge that your calculator is going to start to struggle with it.
Is there a button for factorial? Yes.
Yeah. especially on the TI 83s and 84s. There's one that's on.
Oh, cool.
Good, got it?
Saves so much time and effort.
Yeah. So if you guys plug in 12 factorial, can your calculator handle that?
Yeah.
Try plugging in 25 factorial. What does your calculator say?
5 times 10 to the 25th.
Right, like it starts, and then plug in something like 50 factorial. After a while, your calculator starts to say, this is ridiculous, like leave me alone. Right, you guys get it? So, the good? Everybody else know how to do it as well? Yes? No? What kind of calculator do you have? TI-84. Who else has a TI-84? Yeah, here, let me just do it up here. You guys can walk me. All right. Yes, I'm learning something new today. All right, you guys tell me what do I do. All right, so here's the calculator.
Tell me you don't have.
So you go to math.
I go to math. All right, here I found math. You good with math? Good, math, and then?
Then you go over to it should be prob at the top.
Wait, can you guys even see this?
Not really, no.
Not really. Here, I can fix it. I think I can fix it. I hope I can fix it. Hey!
There we go.
Alright, I go over to what? Prob.
And then you just hit the number 4
It-
when there's a line.
And then I see it right there. Factorial. And then I hit enter.
Yes.
Answer, then factorial. Cool. So let me see if I can do that. So I'm going to do something ridiculous like 900. Let me clear this out. 956. Then math. Prob. 4. It's just error, right? It's like go away. Like it wants to either quit or it wants to go to something else, right? All right, so we're just going to hit quit. All right, so obviously thank you for letting me use your calculator.
No problem.
So obviously if your numbers start to get to be too big, your calculator doesn't like it. So a lot of times what people will do is they'll say, okay, let me figure out my numerator first, plug in the numbers into their calculator, but if that number is too big, they can't figure out that numerator, and then they freak out, they don't know how to solve the problem, right? Even though they knew how to set it up. So here's the thing with this, right? Let's see what's happening right here. I'm going to write out both the numerator and the denominator. So in the numerator, we technically have 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's why that number gets to be so huge. And then down here, the denominator for 3 factorial, we have 3 times 2 times 1. But then we also have this times 9 factorial. So then we have times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. What do you guys think you can do to make this thing a little bit simpler? You can start canceling, right? Whenever you're multiplying stuff in the numerator and you're multiplying stuff in the denominator, you can start canceling stuff out, right? So what we can do here is we can cancel this 9 with this 9, this 8, and all of these cancel. Right, is everybody good with that? Now what we could also do is we could either leave it like this, and this is completely a fine place to stop, because it doesn't really matter how ridiculous your numbers get. Your calculator can definitely handle 12 times 11 times 10. Right? So you could leave it right here. We could go on and simplify it a little bit more, because we know that here 3 times 2 is 6. So we could cancel both of these out, because 6 goes into 12 2 times. So we could simplify this out too. But if you didn't want to do that additional step, you don't have to do that additional step. What I would really just recommend is that you guys leave it as this right here. Because all that we're trying to do is figure out how to make your calculator be able to handle this, and your calculator can definitely handle this right here. Right? So now let me take this right here and rewrite it again, to show you guys that you don't have to write all of this out, Because up here in the numerator we had 12 factorial, and here in the denominator we had 3 factorial times 9 factorial, right? So I'm just rewriting this down here one more time. What you can say then is that 9 factorial is included in the 12 factorial, right? It's like all these numbers are included all up here, right? So what you can do then is you can rewrite this as 12 times 11 times 10 times 9 factorial. You don't have to write out all those other numbers. Divided by 3 factorial times 9 factorial. Right, is everybody good with this? Because now what's happening is, all I'm doing is I'm writing this out just like I did up here. But I realize then that I can cancel all of these out, and I can cancel all of these out. So from here down, this is just 9 factorial. And from here down, this is 9 factorial. So instead of writing them all out, I'm just going to stop at 9 factorial. Because now I know what? I know that this 9 factorial is going to cancel with this 9 factorial. Right, is everybody good with that? And you should always be able to do this on any question. Because if you go back to the formula, here we have n factorial, and here we have n minus x factorial. So therefore here, you know that this number right here, whatever's in parentheses, is going to be smaller than this one up here, right? Because if you take n, you take n minus x. N minus x is always going to be smaller, as long as x is positive, right? All right. So now what we have here is, let me rewrite this right here one more time. We're going to have 12 times 12 times 11 times 10. Divided by 3 times 2 times 1. But now we also have to make sure that we include the rest of that formula, which is 0.3 to the power of 3 times 0.7 to the power of 9. So now this is definitely something that you should be able to handle like your calculator just fine, right? Regardless of the type of calculator that you use. You could even do this with like a dollar store calculator, right? Everybody good with this?
The step that it's covered up.
Yep.
What is that? Is that
This one right here?
yeah? Because I don't know, I'm confused. Because when you cross them all out, it's the same as the bottom one. So do you need to do the step above it?
All I was trying to show is that this portion right here, you can simplify it. Right, you can simplify it to this right here. And I showed 2 different ways to simplify it.
Okay.
Right? The one way that I showed to simplify it is you can write them all out and you can cross them all out.
Okay.
Or if you didn't want to write them all out, you could realize that from here down it's 9 factorial. Right? Because you have 9 times 8 times 7. And from here down you have 9 factorial. So if you didn't want to write them all out, you could just stop at 9 factorial.
Okay. So do you advise that way, just in case of
yeah, the way that I always do it is this.
Okay.
But if you want to do this step right here too, if you feel more comfortable with this step right here, that's completely fine. Sometimes you're gonna have to write out a whole bunch of stuff. Like let's say you had this, right? Let's say that here you had 55 factorial divided by 2 factorial times 55 minus 2 factorial. Let's just stick with that right here, right? All right, you good with the setup so far?
Yeah.
All right. If I wanted to rewrite this, well, down here in the denominator, just for this part right here, I would definitely have 2 times 1, right? And then right here, this is going to be 55 minus 2 is 53. So here, then I would write, okay, 53 times 52 times 51 times. See how it's going to take me forever to write all these things out? And then up here, for the numerator, I'm going to have 55 times 54 times 53 times 53 times 52. See how it's going to take me forever to write these out too?
Yeah.
Well, instead of taking forever to write them all out, and then I'm just going to cross them all out anyways, I might as well stop at 53 because I'm going to cross out all these things anyways.
Okay.
And now all I'm saying here is that from 53 all the way down, I can rewrite this as 53 factorial, right? Because 53 times 52 times 51 all the way down is 53 factorial. And then from here down, I can also rewrite this as 53 factorial.
So you still want to include that, all of the rest of the numbers in, but just with the factorial?
Yeah, exactly, right? So what I can then really just do is I can say, hey, I know that 53, right, I'm gonna erase this, 55 minus 2. I know that this is equal to 53. And if I'm going to have 53 factorial here, and I know that that's part of this, I might as well just immediately say, hey, I'm going to cross all of these out. I'm going to cross all of these out. So let me just stick with 55 times 54 right here, and 2 times 1 right here, and then I'll be done with it.
Okay.
Does that make sense?
Yes.
So what I'm saying is that if we go now back to this question that we had up here, if you feel more comfortable writing them all out and then cross them all off, fine by me.
Okay.
But realize that once your numbers start to get big, you're going to be writing a whole lot and crossing out a whole lot for like no reason whatsoever. So you might as well just figure out what the denominator is. Like here, that this was 9, so you can just write this one down until 9, and then cross those factorials out.
Okay.
Does that make sense?
Yes.
Cool. Everybody else good with this as well? All right. Did anybody calculate this out to see what these numbers come out to be? What is it? 0.277? Everybody good with 0.277? 0.0277? 0.0277? No extra 7. I'll get it right, I promise. Eventually, you guys will help me get there. Oh. 0.04. And then what's points? Oh, that is 0.7 to the 9. All right. So let me make sure I'm on the right track. This thing in the circle, this is this?
No.
No.
0.027 is 0.3 cubed, and then
In the circle is 220.
0.04.
Ah, that makes sense. That makes sense. All right. In the circle is 220 times, and that makes sense. That 0.3 cubed is 0.27, and then 0.7 to the power of 9 is 0.04. So then I'm going to have 220 times 0.027 times 0.04. And did anybody calculate out all this stuff yet? 0.24. Cool. Awesome. Thanks for helping me get there, guys. This was great. It's teamwork. It's another phrase that I taught my 2-year-olds. Teamwork makes the dream work. Yep. So now whenever we set the table, she's like, all right, here's the ketchup. We always give her like the non-breakable stuff, right? Here's the ketchup, go put it on the table. And she's like, okay, Daddy. And she'll grab the ketchup, and as she's going over to the table, I'm always like, teamwork. And she goes, makes the dream work. She puts it up on the table. It's adorable. It's great. Any questions about this example?
Yeah.
Yep.
Could you just do that last part on the calculator instead of crossing it all out?
Do all of this
Yeah.
on the calculator. Yes, you can do this on the calculator. However, like these numbers are going to probably work out just fine. But
right, what you said when they get big.
if they get big, then your calculator starts to struggle a little bit,
Okay.
right? So as long as you're dealing with like the small numbers like this, like you're usually good to go. But if you try to do it step by step, like first calculate out the numerator and then calculate out the denominator with large numbers, it's usually not going to work out.
Okay.
Great question. Any other questions? All right. Then let's do this other example. All right. Take about 5 minutes or so for yourself. question to the best of your abilities. Take it slow. Try to write it out like we did in the previous problem, and see if you can come up with the correct solution. Does anybody need a little extra time? Alright, let's do this one together. On the night before the final exam, 70% of students at a university got less than 8 hours of sleep. What is the probability that exactly 4 of the next 10 students will get 8 hours of sleep or more? So, first, how do we know that this is a binomial question? Only 2 outcomes. What are those 2 outcomes? Either you got less than 8 hours of sleep or you got 8 hours of sleep or more, right? It's only 2 possible outcomes. So therefore, we know that it's a binomial distribution. We're asked to find out what the probability of getting something is, so therefore the formula that we're going to use is the probability of n factorial over x factorial times n minus x quantity factorial, p to the power of x and q to the power of n minus x. Alright, just like we did before, we're going to try to identify what n is, what p is, what q is, and what x is. And if we can identify what these 4 things are and plug them into our formula, then at that point it's just arithmetic. So let's start off with n. N represents the number of trials that we're doing, or the number of things that we're looking at. How many things are we looking at here? 10. We're looking at 10 students, so therefore we're going to look at 10. What are we considering to be success? What are we looking for the probability of what? So let's first, before you give me the number, what is success? 8 hours of sleep or more. That's what we're looking at, so that's what we're going to consider to be success. What's the probability of getting 8 hours of sleep or more? 0.3, right? So here, 70% of students at university get less than 8 hours of sleep. So therefore, getting 8 hours of sleep or more is going to be equal to 1 minus 0.7, or just equal to 0.3. Right, is everybody good with this? So therefore, Q failure is going to be to get less than 8 hours of sleep. And the probability of getting less than 8 hours of sleep is 0.7. And then we're looking for exactly 4 of the next 10 students to get this, so therefore x is going to be equal to 4. Everybody good with this? A very common mistake, and that's why I put an example like this in the notes. A very, very common mistake is that they give you the percentage of one thing, and then they ask you to find the probability that the opposite thing happens. But you use the percentage that they gave you as the percentage of success. Another way of saying that is, they gave you 0.7, so if you put 0.7 up here for P instead of for Q, right? And then you're just doing the exact opposite thing. You are going to see problems like this on the homework, and you are going to see problems like this on the exam. And then there's always going to be the answer choice available to you if you do it correctly, obviously. But the other answer choice is always going to be there too. Like if you flip these, that answer choice is going to be there too. Right? Is everybody good with why here we have the probability of success is 0.3? Remember that success is always what we're looking for. So here what we're looking for is getting 8 hours of sleep or more. So that's why the probability of success is the probability of getting 8 hours of sleep or more. Right? Cool. All right. Now we can plug these numbers in. And we can have 10 factorial divided by 4 factorial times 10 minus 4 quantity factorial, 0.3 to the power of 4 times 0.7 to the power of 10 minus 4. Everybody should be good with that step, right? Just plugging in the numbers. Everybody good with this? If you get to this point, the chances are you're going to get this problem right. Is everybody good with getting up until this point right here? So at this point, we're just doing arithmetic. What did you guys get for this entire thing? Anybody get that? 0.2? Everybody's good with point 2? Any questions about point 2? Did anybody do this the opposite way?
I did it first, but right when we was talking, I caught my mistake, and I fixed it.
And what was did you get down to the numerical answer? What was the
It was
numerical?
like
It was giving you an error, so you knew like
Something was wrong.
Right.
0.037. Cool. Yeah. So if you did it wrong, you should get this one right here. So I'll cross that one out. But those two answer choices will always be there. How do you guys feel about binomial type questions? All right. Just to highlight what we're still going to accomplish with the table, all of these problems that you've seen so far say exactly 4 students, right? You're always given an exact number for x. What we're going to be able to do with this table is, what's the probability that less than 4 students would get 8 hours of sleep, right? So now we're not going to have an exact number for x. We're going to have something that's less than or equal to x. And then we're going to be able to do that with the table here too. We cannot do that with this formula, because this formula is only telling us what the probability is of an exact number for x. But with the table, we'll be able to do less than or equal to or greater than or equal to. But we won't get to that until after we do chapter 5. Just to give you guys a glance ahead of what we're leaving at. All right, any questions about this whatsoever? All right, then we'll call it quits here for today. Have a great weekend.